So we have done so far that a capacitor has two plates and is used to store charge. Net charge on the capacitor is always zero because one plate has positive charge and the other plate will have equal amount of negative charge. Now when there is charge on the two plates and the charge is opposite, then there will be attraction between the two plates. The electrical energy is stored in the form of electrical field because there is an electric field because of positive and negative charges. So this energy is stored in the form of potential energy in the electrical field of capacitor. Now to find out how much this energy is, we may do it in 2-3 different ways. One may be that I take it as a process in which initially, let this be the situation, both the plates are uncharged. Positive charge keeps on increasing on one plate and negative on the other. So I may take this charging of capacitor as a process in which positive charge is transferred from this plate to this plate. So one positive will come here, one negative will come here. Now see, to bring first positive charge, no work will be required because there is no electric field. But now there is some electric field. So if I bring another positive charge here, I have to do work against this field. So one more positive, one more negative. Now the field is stronger. So more work will be done now to bring the third charge and so on. So as more and more charge is transferred from this plate to this plate, a work is done against the electric field to move this positive charge from here to here. So whatever work is done, we can calculate that work done. That will be the potential energy stored in the capacitor. How can we do it? First charge, no work done. Let us consider any one situation when the charge is, say, let us take the charge on either plate at this moment is Q dash. So what will be the potential difference? We know the relation, Q is equal to Vc. So V is Q dash by C. C doesn't depend on the amount of charge, it depends on geometry. So this is the potential energy in this situation. So now if I bring another charge, dq dash, now very important, listen carefully. At any particular moment, I am assuming that this plate has acquired a charge Q dash. We may take it any amount, we may take it X, Y. And I bring dq dash now. See, we cannot simply multiply potential by what is the expression for work done, VQ. Because here V is not constant. It is depending on Q. More charge means more potential difference. So we can't multiply simply VQ and can say that the energy on the charged capacitor is V into Q. Q is the charge on each plate and V is the potential difference applied. No, because V initially is 0 and gradually it keeps on increasing as more and more charge comes on this plate. So we will have to take like this, that at any moment, let us say when the charge is Q dash, the potential difference will be Q dash by C. Now we bring dq dash. So how much work will be done? Let me say this will be a very small amount because we are taking very small charge. V, applying this expression, into Q. So this is just V dq. This is the work done. Potential at this moment is this is the charge transfer. So what will be the total work done in transferring charge? Q. This will be integration of this expression from 0 to Q. what this will be. C is constant, it is not depending on Q, it can be taken out of the integral sign, and we have now and you can use this expression n plus 1 by n plus 1, so it becomes Q square by 2, Q dash square by 2, 0 to Q. Now apply the limits, it will be Q square by 2 minus 0. So it is Q square by 2C. So this is the energy stored in the capacitor having capacitance C when it has acquired a charge Q on each plate. Okay. This can also be written Q square by 2C. What is Q? It is Vc. It is in terms of QC, we can write it in terms of QV, or we can CV also. Or write Q as Vc. So it becomes half CV square. Or substitute C, so it becomes half QV. So it is this, this, or this. This tells us about the total energy stored in the capacitor. Capacitor is actually just like a temporary battery. Okay, we may have some other approaches also to derive the same expression for the potential energy. I may briefly give you an idea because that may be used in some other problems also. Here we can use the concept of force. One positive plate, another negative plate, so there will be a force between the two plates. And how much that force will be? Suppose I want to calculate the force on this plate. Q into E. Whatever is the charge here multiplied by the electric field. And what is the electric field produced by this here? Sigma by 2 epsilon naught. Right, this is the field. If I take a point P close to it, how much is the field? Sigma by 2 epsilon naught. We have used Gauss's theorem to prove it. So this is how. Where sigma is surface charge density. So I can write that again in terms of so Q square upon 2 epsilon naught P. This is useful for many other calculations also. This tells us about the force on each plate of capacitor because of the other plate. Now I can assume that initially the distance between the capacitor's plate is almost 0, and then we gradually increase it. These plates are attracting and I am moving them apart. So naturally some work will be done by me against this attractive force. Whatever work is done, that is actually stored as potential energy of the capacitor. So how much work will be done? If I say distance from 0 to D, so work done will be simply F into D. Q square 2 epsilon naught A into D. So this will be the work done. Q square 2 epsilon naught A by D. For a separation D between the plates and area A. Now what is epsilon naught A by D? This is C. So I can write it Q square by 2C. So again the same expression. This is also one of the way of doing it. Now how do we know if we have a capacitor actually? We are saying it is just like a temporary battery. What will happen if I connect to a bulb? These electrons will start moving. This one electron will move like this, coming here, so the bulb will light, and will move here, neutralize. It will neutralize one positive. So it has certain brightness. Okay, now the potential difference has reduced. So let me say its brightness will decrease. Another electron moves, and now it is going to this plate, neutralizing one positive. The potential difference is further reduced now. And then one more negative. This continues till the capacitor is fully discharged, and once it is fully discharged, this bulb is off now. No more movement of electrons because we don't have those imbalances. So it means if I connect a bulb, initially when the capacitor is fully charged, potential difference across this is maximum, and it decreases and then it becomes zero. We can calculate the potential energy stored in the capacitor using this concept also. Here again, how much charge is transferred, what is the potential difference, we will get again the same expression, half CV square or Q square by 2C. So this is about capacitor. We can find out the potential energy by using these 2-3 concepts. I also told you how can we calculate the force between the two plates if required. One more concept which is asked and very common. Positive charge here, negative charge here, and this is connected to a battery of potential V, EMF V, okay. And when the capacitor is fully charged, and this is the situation now. Capacitor fully charged means this is V, this is V, so no more movement of electrons. Basically, whenever, if I connect a key, when I press it, electrons move to this plate. Induced charge comes on this plate. So, and after the capacitor is fully charged, and the potential difference between this becomes V. As soon as minus charge comes here, plus here, the potential starts increasing, and the moment this potential equals this, now the movement will stop. So if I connect again a bulb here, initially the brightness maximum, but when the capacitor is fully charged, it's zero, because it is just like two batteries, 5 volts here, plus minus, and 5 volt here, plus minus. So if I connect any bulb here, the brightness will be zero. No current will flow. Okay. If the capacitor has charge Q and the potential was V, so how much charge has been supplied by the battery? Q. How much work has been done by the battery? Q into V. This is how we calculate. Q charge supplied and potential difference was V. And how much is the energy stored here? Half QV. We have just done. How can we apply the conservation of energy here? Where has this energy gone? QV, the work done by the battery. Half QV is the energy stored in the capacitor. So this is, actually there is a loss of this energy. Where is this energy going? See, in the process of charging the capacitor, electrons are flowing through these connecting wires. And when the electrons are flowing here, they are collecting on this plate. So whenever electrons flow through a wire, it is current passing through a wire. Wire gets heated. So this energy, half of the energy, is going basically as heat energy and also radiated as electromagnetic waves. So this energy, half QV, is stored in the capacitor and half QV as heat or electromagnetic radiation.